All right, let's start with a calculator problem here. Okay, so working off of the morning review session, part 2, calculator portion. It says an object moving along a horizontal line has a velocity function t cosine of pi t over 6, measured in inches per second from 0 to 11. Create sign line for velocity and acceleration. I won't ask you to create sign line for acceleration. So, I mean, we're going to have to eventually do that down the road, but not on this test. So we can ignore this piece here. Okay, so go ahead and put this velocity function into the 84. Oh, and then you can, on the 84, for some of the calculators, you can get to the fractional math print if you do alpha y equals. If you do alpha y equals, get to that n over d, get that nice math print. Okay, pi t over 6. Remember, we're always using the variable x. Okay. Now, normally I would do zoom 6, but we are stretching from 0 to 11. So I want to give myself room to do that. So for window, you can always adjust how far left, how far right, x min, x max, and you can also adjust how far down and how far up your graph goes. So 0 to 11, I guess you could do zoom outs, but I'm just going to say from -1 to 12 so I can see around the edges a little bit. And then after this, then I can do zoom box, or I can go to a zoom within a box to see how that looks. Okay. Create sign line for velocity. So I know I'm looking for x-intercepts. That's when velocity is 0. Those are my critical points.
Mr. Yang?
Yes.
Why did you make the x max 12 in the window?
Oh, just because my x value is from 0 to 11. So I just want to see around.
Oh, okay, okay. You did it based on the range.
Right, based off the range. Okay. But I mean, you could just as easily do zoom 6, and then if you want to zoom out, zoom in from there. I just wanted to play with x. So you can always play with your x min, x max. Don't worry about the scales, but if you can always play with these to get specific values if you like.
And what do I click after that?
They just hit graph.
Okay.
So I'm looking for x-intercepts. I'm going to hit start with trace first, just to kind of get an idea where it's landing. So it looks like it's landing around 3, 2.963. But it's just not exactly accurate, right? Because I'm just moving my trace, and the trace is not hitting exactly right at y equals 0. So I have an idea, right, around 8.9. So we know how, in the ballpark range, where our x-intercepts are. So now let's get more accuracy here. So we can gain more accuracy if you do second trace 0. So second trace 0 means I'm going to look for that x-intercept. Left bound. So I'm going to pick a point to the left of the x-intercept. Because right now I want to target. So that's safely to the left of the x-intercept, hit enter. Now it's locked in, right bound. So we're going to tell the calculator on a point on the other side of the x-intercept, hit enter. Now it says guess, so hit enter a third time, and now it's going to accurately find that x-intercept for us. So it looks like it's exactly at 3. Okay. And we can repeat the same process here, and we're going to get exactly at 9. And we can clearly see where the graph is above and below the x-axis. So this is positive velocity, negative velocity, positive velocity. So it's moving right in this interval, moving left, and moving right in this interval. Okay. On the 36 Pro, table, edit function. Always use variable x. Make sure you're in radian mode. Start, I'm going to start at 0. I'm going to step by relatively large step, 0.5, so I don't have to scroll through too much. I just want to see where my value is going to change sign, where my velocity is going to change signs, and that's going to tell me where these values are. So I'm looking to see where it changes signs. Right now it's positive. When it's going to go back down to a negative, okay, right here. And it's landing right at a y-intercept for us, so landing right at 3. We don't have to go to a decimal value because it's perfect right there. So that's 1. Still negative. Let's see, when is it going to change from negative to positive? Still negative, still negative. Oh, negative positive here. And it lands right at 9, so that's nice. But if it's at a decimal value, what you can do is you can go back to table, edit function, and then you can decrease the distance of the steps. That will kind of give you more accuracy if you're trying to make a better approximation. But in this case, it's landing right at a whole number. Now, to determine the signs, we just look at what the signs are, right? So between 9 and 11, those are all positive values. So we know that in that interval it must be positive. Between 3 and 9, all the values that we see are negative, so we know it has to be in the negative region. So 36 Pro just requires a little bit more kind of visualizing because you don't have the graph in front of you. Okay, part B, find the times when the object is motionless. Okay, we have them right here. Yes, hold on. See, technically, I think even 0, right? So 0 is part of my bound here. And yeah, because 0 is part of my bound, I need to include 0 as well. So motionless at t equals 3, 9, and 0. And if I ask you for a reason, then you would say because velocity is equal to 0. Okay, question?
Yeah, when I'm graphing it and then I do second trace 0, get left on right bound, I have x equals 9 and y equals 9e negative 13.
Right, okay, good. So when you see this negative 1e to negative 9, that's a really, really small decimal number. That's basically 0. So if you see that, just think of it as 0.
Okay.
It's a, for some reason, it doesn't round to 0, so it just gives you that really, really small decimal. But yeah, don't worry about that. That's basically 0.
Okay.
Okay. Okay, any questions so far? Okay, part C, find the velocity at t equals 4. So we have the velocity function stored under y1. So I'm just going to call the velocity function vars, y vars function, parentheses 4, sorry. And I get negative 2. .36 Pro, go to table, edit function. I'm sorry, table function, because we're ready to call it. No need to make any changes. Just plug 4, because this is my velocity function, negative 2. Units of measure, if I ask you for it, in this case, inches per second. Find the acceleration at t equals 4. So acceleration is the derivative. So derivative, I'm going to access math 8. Again, I'm calling my function here. So this is going to take me down to acceleration, and then it's going to plug 4 into the acceleration function. Same thing here. Use the derivative feature, call the function. Now, when you do f of x, make sure that you're closing your set of parentheses here. That's something subtle that will complain if you don't close the parentheses. So you got to close the x, and then so 2 sets of parentheses. Okay. Units of measure, inches per second squared, right? We're finding the rate of velocity, so we're going to add another time component to it. All right, any questions so far? Yes.
Sorry, I missed it, but for the sign line, did you just plug in and see where 0 was? Or...
Yes, that's right. Well, which one are you using, the 36 Pro or?
Yes.
Okay, yeah, if you use 36 Pro, yes, you're going to go to table, edit function. I'll start at 0. I started at a relatively large step, and yeah, and I'm just looking for 0.
The changes.
That's right, change in sign. Good.
Okay.
But it just so happens that this is my x-intercept is landing at a nice whole number. Usually it's not as easy as this. If it's not as easy as this, then you're going to decrease your step and then keep finding a better approximation.
Okay, great.
Yeah. And then I know positive and negative intervals because I'm just looking at the signs in between these intervals to correspond with the signs of those, yeah, plus or minus. Okay. All right, part E, is this object's speed increasing or decreasing? So increasing, decreasing speed, we look at the signs between velocity and acceleration, right? Same signs, so speed is increasing. Because velocity, acceleration have same signs.
You kind of already found acceleration to solve E, would you need to solve for acceleration?
Yes, that's right. If I did not ask you for acceleration and I asked you for increasing, decreasing speed, you have to find acceleration, right? We got to have both information to find increasing, decreasing speed. Okay, let me add to this problem here. What if I ask you, is velocity increasing or decreasing? Then how do we make that determination? Just acceleration, right? Don't let that velocity word throw you off. You see the word increase, decrease, that's changing the meaning of the question. So velocity increase, decrease, we just look at acceleration. We say that velocity is decreasing because acceleration is negative. All right, questions so far? Are we good? All right, part F, find the total displacement. Displacement is just definite integral. And I'm looking for notations here, so you don't have to write the function out, but show me that you're taking the integral of, in this case, of the velocity function. Math 9. Call the function. The reason why we're getting negative is because between 0 and 11 seconds, the progress that this particle is making, this object is making, is in the backwards direction. So it's going to gain more ground moving left than it is going to go right. So that's why we're getting that negative displacement. Okay, integral notation. You can type in the function, or if you have it stored, just call it under f of x. X, close parentheses. Okay, questions with displacement. Also, notice what happens to velocity, right? Displacement, when we take the integral of something, that unit is going to change. Velocity was inches per second. And basically, what we're doing is we're multiplying by time. So what was inches per second multiplied by second is going to end up losing that, that time component, moving up. So we can think of it as area, right? This is kind of like an area component, inches per second times second will just give me inches. So integration and derivative, your notation, your units are going to change. All right, total distance, same as displacement. We just need absolute value bars around V of t. Make sure you put the absolute value bar in the correct location, just around V of t, and not around the entire expression. All right, this will be wrong. Call the absolute value, which is stored under math, number, ABS. And it takes a while for absolute value calculations, especially on the 36 Pro. math, number, ABS. Okay, I get 34.844. So my total distance, because of all the back and forth movements that this object is going to achieve, it's going to have a total distance of 34 inches. Okay, find a time when the object reaches minimum velocity. So basically, you're just going to be scrolling down and finding where your velocity is at the lowest point. And if you're on a 36 Pro, you're just scrolling to see when is your table of values reach the lowest y value. I just want to give you some idea. I won't. This is not on the test. But anytime you're looking for minimum velocity, you're just literally looking for the lowest point, looking for the valley of your velocity graph. And on the 36 Pro, the way you find the valley of your graph is you just look to see when does my y value decrease to the point that it suddenly reaches its lowest point and then starts increasing. Then that's when you know that's when you've reached your minimum. Okay? But for now, we'll skip this here. Given initial position equals 3, find the final position of x equals 11, x of 11. So this is using that final position formula that we've been using. It's on your formula sheet here. Anytime I'm looking for a final position.
Mr. Yang?
Yes.
So are we just not going to do the minimum velocity?
Right, we're not. But I just want to kind of give you an idea down the line. If you're looking for minimum velocity, you're just going to look for the valley of the graph. You just have to kind of scroll your way down. Yeah, but we'll we do need to eventually get around to this, but not on this test. Okay, final position equals given position or initial position plus displacement. So formula x of b equals x of a plus integral from a to b of v of t dt. I'm looking for x of 11. I have x of 0. So I'm starting at time 0. I'm ending at time 11. I want to know how much ground did I gain between 0 and 11 minutes or seconds. So I need to find the displacement between those two time periods. Where I started and how much movement I made between those time periods. Okay, make the calculator do the work there for us. Oh, we already have this information, right? Okay. We gathered it from part F, but I just entered it again. Questions so far? All right, part K, find average velocity. So this is average value theorem. One over b minus a, integral from a to b of f of x. But instead of f of x, we're doing velocity here. So 1 over 11 minus 0, integral from 0 to 11, v of t dt. Okay, so this is a repeat information, right? I could enter it again, but I already kind of found it from here. So let me talk about the units here. Velocity is going to turn itself into inches, right? But it's going to go right back to inches per second because we're dividing by time. So the integral is going to push it to inches, but then we're coming right back to inches per second because we're dividing by 11 inches per second. Okay, don't worry about this part here. Find the time when object reaches average velocity. We'll have to, yeah, maybe we'll come back to it later. But won't be on this test. Okay. Any questions here? You won't see a problem like this. Okay. We eventually do need to do this, but not on this test. Table of values. I think I'm gonna skip this one here just because we did yesterday. I want to focus a bit more with maybe we'll do an even odd function. We'll do a u substitution. Okay. So I'm going to go over to morning review here, and let's look at number 3. We haven't done absolute value for depth integrals, so we're going to come back to it. This is omitted here. Let's look at number 3 here. Okay, this is off of the morning review, non-calculator. All right, first things first, we ask ourselves, is this something that we can handle just by power rule alone? All right, there's too much going on here. And if I try to move this, it's not, this is way too much. So we know that expansion alone is not going to be able to handle, right, if there's only one term in the denominator, then we can bring it up and we can distribute it through or separate into fractions, but this is too much. So we have to explore u substitution, but for u substitution, we need a set of parentheses. So how can I rewrite that? Denominator to the 1/4. Okay. Having a set of parentheses is helpful because it kind of helps us focus in on where our u value could be located. Okay. Inside the parentheses.
Mr. Yang.
Yes.
So since the x minus 2 is not in parentheses, do we just not use it for u substitution?
That is correct. Yeah, we're hoping that this x minus 2 will go away on its own. And technically, yes, you can have a parentheses here, but usually we want to choose the u value that is within a complex expression, a more complex expression, and where the parentheses is necessary. And also, we see a higher degree, so that's already making a better candidate for our u value than the x minus 2. Because the higher degree, we're hoping it will handle this numerator degree. Okay. Du dx. Cross multiply. Divide by 2x minus 4. And we make our substitutions. Just these portions here. Dx becomes du over 2x minus 4. Okay, we're making some progress. We see some x values go away, but now we're trying to handle this here. What do you think we can do to get this to hopefully match up and go away?
Factor.
Good. All right, let's take that 2x2 out of that denominator term, and maybe we can get a better match here. So if I factor 2 out, 2 parentheses x minus 2, now perfect match. Right? Now I can get my x minus 2 to cancel out. So that was the hope. The hope was that we didn't quite know, we didn't quite have something for that x minus 2, and we were hoping that our derivative will handle it. So this goes away, this goes away. There's a 2 left over. Push it out in front. That's 1/2. So our problem looks a lot cleaner. Are we ready for power rule?
Does the u have to go on top?
Right, that u is still a little bit out of place. We're almost there, but we can't do power rule if our variable is out of place. All right, move to numerator. Now we're ready. Keep the coefficient, add 1 to the exponent. Negative 1/4 plus 4 over 4 is 3/4. Flip that complex fraction below. I get 4 over 6, which is 2/3. And remember, if you're going through u substitution, u is only a temporary variable. You got to bring it back to your original variable. Okay, questions? All right, let's do a definite integral one. Number 5. Okay, when you see definite integral, don't let that be the first thing you do. It's the last thing we do. Okay? The first thing we do is we're going to pretend like the bounds are not there and handle the indefinite portion of it. And then we can turn around and figure out what to do with the bounds after we take care of this problem.
Shouldn't we switch them because it has to go from lower to higher?
You could, okay, you could. I would say that only switch if you're having to read a graph. If you're having to deal with maybe even or odd functions, or you want to be able to picture a graph,
Okay.
then I would flip. But you're welcome to flip. You're always welcome to flip, but just make sure you pull a negative out. But if I'm doing it through just algebraic method steps, first theorem, everything will work out in the end anyways. But I would say you can flip if you want, but I would say only do flipping if you're having to actually work off of a physical graph that you're trying to read. Yeah, that's my suggestion. All right, so we're here. Can we just rely on expansion? Or is this not enough? Yeah, we can't, right? Too many terms inside the radical. This is unresolved. So use substitution. Let's get a parentheses to show up.
Mr. Yang?
Yes.
So if you have like an exponent, usually you're going to want to use substitution, right? Like in this kind of problem?
Yes.
Like 1/2 and stuff like that as an exponent?
Yes. But just be careful because not every exponent is going to be a use substitution problem. So we really have to kind of explore whether this is doable or not. So let me give you a quick example here. Something like this here. Even though this is square roots, the square root is relatively clean. It's just x to the 1/2. So this is nice and clean. We can distribute through. We can bring that up to the top, distribute through, and no worries here. No need for use substitution, even though there's a parentheses and there's a square root. Because there's no addition and subtraction within the square roots, we're safe. We don't have to rely on a messier rule because this is nice and clean. We can distribute through. Yeah, so always explore your power rule conditions first. And if it's too complex or if it's a problem that exponent is too high, then your second option is use substitution.
Okay, thank you.
Yeah, but not every problem with the square root and parentheses is a use substitution problem. Okay, U value. X's cancel out. Power rule. No need to have plus C because now we know that we have bounds to worry about here. So we have two options here. Leave it in terms of U, convert the bounds. So I'll do both methods and you can choose which one you want to use on the test. My conversion is through this assigned expression between U and X. So my lower bound was square root of x. Sorry, square root of 7. Then u is equal to 16 minus square root of 7 squared, which is 9. Converting my bounds, if x equals 0, then u is equal to 16 minus 0, which is 16. Everything's in terms of u, so root 7 becomes 9, 0 becomes 16. Now you can plug in. I'm not going to require you to simplify, so as long as you have some version of the answer, I'll be happy. But you can go all the way down if you like. But either is acceptable. As long as you give me a numeric, as messy as it is, I'll take it. Method 2 is where we do everything in terms of x. So we take our antiderivative, we go one step further, get that u in terms of x, and if you do that, then you can use the original bounds. No need to convert the bounds. So if you give me your answer in this unsimplified form, I'll accept this as well. But if you leave it in this form, then that's not good enough. Okay, you need to show me that you understand how to plug these values in. You can leave your answer in unsimplified form, but you got to get to at least this part. Okay, questions? Let me do a variation of a trig integral here. So this is not on the worksheet, but I'll call this 6b here.
Mr. Yang?
Yes.
So the graph on top of the non-calculator worksheet, is that like the velocity graph question you'll give us in the test?
Wait, this one here?
Yeah. Like, see with the graph.
This one here?
Yeah. Because you said velocity graph question, and just trying to think of an example.
Right. So actually, the velocity graph is going to look more like this here. And then I'll ask you for final position.
Oh, so it's like a short question?
Yeah, it'll be a short question like this.
Okay.
Yeah, just this. Okay, let's try this one here. Is this something that we can handle just using a rule here? So, too messy, right? We don't have a rule that can handle this. But we do have trig rules, right? We do have a trig rule that looks like this, the integral of sine of u du is equal to negative cosine of u plus c. So maybe we can target this. So if we want to target this, then what's our u value? What's our u value? That's right, the entire expression. So we're going to target this. We don't know what's going to happen here, so we'll just see what happens when we go through and see if things can clean up. I'm going to rewrite this as 1/2 x to the 1/2, just to get it a little bit cleaner. All right, du dx. Keep the 1/2. Derivative. Clean this up. Try to get dx by itself. 1/4. This x to negative 1/2, I'm going to push it back down to the denominator, and I'll convert it back to square root of x, but you don't have to. But there's square root of x here, so maybe it'd be easier to match. Cross multiply. And no need to move anything over. Our dx is already by itself. So let's see what this looks like after I make my substitutions. So u is going to go here, and du over 4 root x is going to go there. I haven't dealt with this issue yet, so I'll bring everything else down that I did not underline. All right, what do we see? Yeah, so this is our goal, right? We need to get here, and thankfully, our x's do cancel out. Push the 16 out in front, 4 times 4. Perfect match. Now we can apply our rule. Oops, negative 16. One more step. Our u is a temporary variable. Let's bring our u back in terms of x. All right, let's do a second fundamental theorem problem here. This is number 8. Find the derivative of the definite integral from negative 4x to root x of 1 minus t squared dt. This looks complicated, but this 1 minus t squared is not going to change a whole lot because we're doing 2 operations that are going to cancel each other out. The only thing we got to keep track of is the upper bound and a little bit of the derivative. So we plug the upper bound in for the t's, multiply by the upper bound's derivative, and because the lower bound is also a variable, we need to repeat that process below. So the rule looks like this. plug the upper bound into the variable of the function, multiply it by the upper bound's derivative, minus lower bound into the function times lower bound's derivative. Square root of x is really x to the 1/2. Do the derivative here. Lower bound into the variable. So if there are multiple variables, you're going to plug this into all the t's. But in this case, there's only one. Times the lower bound's derivative. Just clean up your negative exponent. I'm not going to ask you to clean up much further than this. If you have some version of the expression, that's good enough. I'm not looking for common denominators or anything like that. If you have a couple of terms still left in parentheses, I'm ultimately seeing if we understand how to go through this process. So really anything that comes out of it, as long as you have all the right pieces, that's all I need. All right, any other questions? I think first period needs to start getting ready for their test.
On number 4, an absolute value one.
Yeah, don't worry about the absolute value. I won't give you an absolute value for integral problem. We haven't done that in class yet, but we will eventually come back to it, and because it is something that is feasible on the AP exam, so we'll come back to it. But yeah, no, we can omit number 4 here. All right, good luck, everyone.
Mr. Yang,
Yes.
could you go back to number 7?
Yeah.
Thank you, Mr. Yang.
All right, see ya.
Like the number 7 you did, yeah. Yeah, so
oh, this
I was
one.
a bit confused. Like I was trying to do it in my head, like when you took the derivative of u.
This one here?
Yeah.
Okay. So the derivative is x to the 1/2 becomes 1/2 x to the negative 1/2, right?
I thought you add 1. Or is that antiderivative?
That's antiderivative, right?
Oh, okay, okay. That makes a lot more sense.
Good, good.
Okay, I understand.
All right, see you guys in class.
Thank you.
See you, Ms.
Bye,
Lang.
Joko.